So this quiz, in theory, is all review still. In fact, Physics 12 is going to begin, in my mind, today. Today is going to be really the first brand new, hey, I didn't see anything like that at all last year lesson. We'll get about halfway through the maybe all the way through the lesson. I'm optimistic we'll get all the way through. Good old Anne. Skydiver is in free fall. I've mentioned I jumped out of an airplane. He's been falling long enough to hit terminal velocity. Okay, that's a key concept. In other words, he's no longer accelerating. Which of the following statements is true? There are no forces acting on the skydiver. No, gravity is acting on him, as well as another force. So false. Half mark for each of these, by the way. The magnitude of the gravitational force is equal to the magnitude of the force of air resistance. Yeah, that's why he's no longer accelerating. The net force is equal to 0. Yeah, because that's another way of saying he's no longer accelerating. The skydiver is slowing down. No, then he would be accelerating. Decelerating, but he'd still be accelerating. Half mark for each of those. So that's out of 2. Find the acceleration of the entire system if mu equals 0. You know what? I'll bet you at number 2 there's going to be no friction. I'll bet you number 3 is going to be the same question, but with friction. So I said, okay, I got m1g, normal force, number 1, tension, no friction. m2g, normal force, number 2, applied force, tension. Said, okay, what's my equation going to be? Winner minus tension plus tension minus loser plus winner equals m1 plus m2 times A, or m both times A. Losing tension. Always good. Looks like A is going to be F applied divided by m1 plus m2. It's going to be 45 divided by 10 plus 15. It's going to be 45 divided by 25, which is 9 divided by 5. 1.6? No? Am I off? 1.8? That's what I said. Yeah. 1.8 meters per second squared. If you got that, 2 out of 2. Otherwise, I would probably go half mark if I saw that, half mark if I saw that, half mark for sticking in the numbers, and a half mark for the answer. And if you forgot the units, take a half mark off. B, find the tension. I'm going to look at mass 1. It's going to be tension equals m1a. Or if you wanted to, you could go applied minus tension equals m2a, whichever, but I'm going to use the first method because I think I can do this in my head. It's going to be 10 times 1.8. I think tension is exactly 18 newtons, yes? And that gets you 2 out of 2. In terms of part marks, I give you 1 mark for the equation, half mark for the numbers, half mark for the answer. Number 3, repeat, but this time with friction. Oh, and the applied force is increased to 60. Why? Because 45 wasn't enough to get it moving, which made it a pretty boring question. Turns out when you added up both of the frictions, they added up to more than 45. Okay, so I would then add friction force 1 and friction force 2. That arrow really looks like it's slanting up, which is not good. Let's try that again. That's better. My equation would look like this. Applied minus tension minus friction force number 2 plus tension minus friction force number 1. That equals m1 plus m2 times A. Once again, I lose tension. Woohoo! And they said, find the acceleration. So I'll get the A by itself, which means I think, Jacob, I'll divide by m1 plus m2, and it's going to be the applied force minus mu times normal force number 2 minus mu times normal force number 1. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. It's going to be applied, which was 60, minus mu 0.12 How big is the normal force in this diagram? By the way, that answer is going to be changing after today. But for now, it's still M2G. It's going to be M2 15 times 9.8 minus 0.12 10 times 9.8, all divided by 10 plus 15. How big is the acceleration going to be? Bracket 60 minus 0.12 times 15 times 9.8 minus 0.12 times 10 times 9.8, close bracket, divided by, open bracket, 10 plus 15, close bracket. Do you get 1.22? 1.22? Is that right? If you got that right, 3 out of 3. Okay. Otherwise, I would probably go 1 mark if I saw that, 1 mark if I saw that, half mark for the numbers, and a half mark for the answer. I bet you part B says find tension. It does. I couldn't fit that on the first page. I tried, but I couldn't fit it with the graphics. It says find the tension between the two masses. Okay. I'm going to pick the one where tension is the winner. I'm going to use mass 1 again. My equation is going to look like this. Tension minus friction 1 equals M1A. Or you could go F applied minus tension minus friction 2 equals M2A. Why bother? Pick the one where tension's the winner. In fact, I would now, Anthony, say tension equals M1A plus friction force number 1. I would now say tension equals M1, which was 10 times 1.224 plus 0.12 times 10 times 9.8. Tension is having to accelerate the block and cancel out friction is really what we're saying. It's going to be 10 times that number plus 0.12 times 10 times 9.8. Please tell me, is the answer 24 even? No? Am I wrong? 24 even? Some feedback would help. There we go. Sensing people. That's because you, instead of using your answer button of 1.224, you just use 1.22. Why round off if I have it stored on my calculator? So you went like this, 10 times 1.22 plus 0.12 times 10 times 9.8. And I'll give you full marks for that. 23.8? Did you use 1.2? Don't round off that much. So if you did this, I'll give you full marks, but you see the difference it's already starting to make? You have the answer button on your calculator. Use it. It's handy. It's less typing. Otherwise, I would probably give you a half mark for that, half mark for that, half mark for the numbers, and a half mark for the answer. Mr. Jude, any suggestions on how I might want to solve these here elevator questions? Would it be wise to try and like memorize a different approach for each one and just do these in my head? Or the 1 whole second of work that it takes to write a free body diagram, do you find that makes things clear up very nicely? I have a convert maybe. So we have an elevator question. They want me to find the scale reading, and you know what? They want me to find the scale reading in newtons, so I don't have to divide by 9.8 to convert it to kilograms. How nice. Here is this person. What are the forces acting on him? I got gravity down. I got normal force up. Bigger, smaller, or the same size? Well, if we're accelerating up, my equation is going to be normal force minus gravity equals ma. It's going to be normal force equals ma plus mg. It's going to be m 75 a 1.2 plus 1.2, Mr. Dueck? 1.6, sheesh. 75, 1.6 plus 75 times 9.8. Is it 855? No, yeah? Yeah, okay. 2 marks for that if you got it right. Half mark if you got the right newtons. Otherwise, I would give you 1 mark for that, half mark for that, half mark for the answer. Accelerates downwards. You know what? That's going to be a different free body diagram. That's going to look like this. The normal force is going to be smaller. My equation is going to be gravity winning, normal force losing, ma. My equation is going to be mg minus ma equals Fn. Fn is going to be m, 75, g, 9.8, minus m, 75, g, 9.8. Running out of room here, Mr. D. Let's get clever. Let's move my free body diagram over there. Ha-ha! 75 times 9.8 minus 75 times... I wrote 9.8 twice, Mr. Dueck. How about put the acceleration there instead of 9.8? 1.25. At least I caught that. Minus 75 times 1.25. Hey, is the answer 641? Newtons. Newtons. Same as before. I'd give you probably 1 mark for that, half mark for getting the Fn by itself, and a half mark for the answer. Is that okay? You looking puzzled? Approach wrong or sloppy calculator work? Think about it. Oh, by the way, if I asked you to draw free body diagrams and I was giving you marks, I would definitely look for, in this case, a normal force that was shorter than mg, or in the previous case, a normal force that was bigger than mg. C, the elevator moves up at a constant velocity. Moves up at a constant velocity. Okay, if I'm moving up at a constant velocity, who's winning? Well, actually, because it's a constant velocity, Ben, it's a tie. But let's prove it. Let's assume Fn is winning. We would go like this. Winner minus loser equals, but why would I write a 0 there? Acceleration is 0. Ma is 0 because constant velocity, which means really, Alex, I could do this. And believe it or not, this is part of what led Einstein to his theory of general relativity when he started to say, you know what? We have no way, there is no way in the universe to tell whether you are all right now actually standing still or if you're traveling in a straight line at a steady speed. It's all relative. We don't know. There's no measurable way to prove it. We could, in fact, you know what? Are we actually standing still? How? Okay, the Earth's spinning. What else? Solar system itself, or the Earth is revolving around this. What else? The solar system is moving through the Milky Way. What else? The Milky Way is tumbling through the galaxy. What else? Our galactic cluster, and these are at huge astronomical speeds, but the speeds are constant. We can't tell. The only way we can tell that we're moving is we look in relation to other observed astronomical bodies. But we could be standing still and they could be moving, which is what they thought for hundreds of years when they felt that the sun revolved around the Earth. Nerd moment over. Oops, try that again. 75 times 9.8, probably 73.735, right? Jake, was it D that you wanted to ask me about? Oh, it's C? Okay, lovely little proof there. What about D? Well, I would go, okay, definitely mg. And this is where kids are, you know what, Mr. Dueck, I'm not sure. Maybe he's weightless. Let's pretend maybe there is a normal force. I'll draw a small one in there. But clearly, if he's accelerating downwards, who's winning? Gravity. Who's losing? Normal force, and that equals ma. mg minus ma equals Fn. 75 times 9.8 minus 75. What's my acceleration? 9.8. That's a proof of why it's 0. If you knew enough to just say 0, you get 2 out of 2. But there's the free body diagram algebraic proof. This is why you feel weightless. Are you weightless? Is why I said I called the normal force. I said it's your apparent weight. Right then, even though mg is still acting on them because it's in the equation, they would feel as though there was no mg. They would apparently feel weightless even though they're technically not because weight is mg. Can you give yourself a lovely score, please, out of 19 on the top of the quiz? Any lawyering with me? Now is the time. So we said the idea behind the Atwood machine was it's a massless, frictionless pulley. It's massless, frictionless ropes, but it's 2 masses. And this allows us to do some thinking with multi-body problems. Example 3 says this. Consider the following system. Which of the following is the best force diagram for mass M2? Let's see if we can reason our way there. Let's draw the forces on mass 2. What are the forces acting on mass 2? Get the obvious one. I agree. I'll call it M2G since they called it mass 2. A normal force. What else? Which way do you think mass 2 will accelerate? To the right. So there has to be a force unbalanced that way. It's not the applied force. And here's how I know the applied is a good guess, and kids always guess applied, but applied force is touching mass 1, not mass 2. Ah, so the push is coming not actually from the applied force, it's coming from mass 1. And I realize the reason mass 1 is pushing is because of the applied force, but we're looking at mass 2. You know what? Let's call that a contact force. When 2 surfaces are in contact with each other, they push against each other. Yesterday with my glass book example, I called it a normal force. The only problem is I already have a normal force pointing up. I don't want a normal force pointing sideways. Hey, what's the best free body diagram? A, B, or C? Okay. Now, why would C be wrong? If C was correct, could this thing be accelerating to the right? No, because I have balanced forces and balanced forces. So that's got to be wrong. If B was correct, you know what? A lot of people pick B because they so want the applied force to be on mass 2. No. What's pushing mass 2 sideways is this contact force. What's pushing mass 1 sideways? Oh, hey, what if we drew the free body diagram for mass 1? The free body diagram for mass 1 would have that. There would be a big force F applied, and there'd be one more. Because forces come in pairs, whatever the contact force against mass 2 was, there would also be a contact force against mass 1. It would be the same size. I drew it shorter in my picture on the left to emphasize that the winner is F applied. But what this means is, you know what? I think maybe I can deal with this, with these many body problems, even when there's no rope. Says explain your answer using relevant physics principles. You know what? It's a good free body diagram. We just did. So, this is tougher than physics 12. Sorry, this is tougher than physics 11. Forces in a couple of directions. Says find the acceleration of the system and then find the contact force between the 2 blocks. Okay. Any suggestions on how we should start? Oh, please, God, let them have an immediate suggestion on how they should start. And free body diagram, or you know what? Did they give me a lovely picture? Let's label the forces right on the lovely picture, which technically isn't a free body diagram, but okay. What are the forces on the 6 kilogram mass? Get the obvious one. So let's call this what else? What else? Well, we have this applied force pushing to the right, but since I noticed there's another one, I'll call this F applied number 1 to go with mass number 1. Make sense, Anthony? What else? Nope, second applied force isn't touching mass 1. Ah, there is going to be a contact force right here, so there's going to be, I think, F contact pushing to the left. Darian, I could have drawn it right here, but technically, look up. I could have drawn it right there, but for a free body diagram, even for labeling the forces, your forces are supposed to kind of come from the middle of the object to show that's where it came from. And I'm telling you that 6.75 is not touching the mass 1, the 6 kilogram mass, so it's not on it. Let's draw the forces on the right-hand mass. Get the obvious one, M2G. Normal force number 2. What else? We have F applied pointing to the left. Oh, F applied number 2. What else? And this is where we're going to use, because there's 2 masses, we're using Newton's third law that forces come in pairs. We're going to say, you know what? There's also a contact force to the right. And it's the same magnitude. It has to be. When 2 objects push against each other, the forces are equal and opposite. That's the, for every reaction, there was an equal and opposite reaction. Friction? Friction, yes or no? And how do you know? Oh, mu 0, so we're on ice. By the way, if we did have friction, I'd just have a couple of more forces I could deal with. But I'd have to have them pointing in the right way. So before I drew in friction right now, I would look at what I have and I would say, okay, are we accelerating to the left or are we accelerating to the right? And there was a way you should be able to figure this out. How do you know? The 42.5, I did that deliberately, is way bigger than the 6.75. So who's winning? Anything, Sarah, that ends up pointing to the right. Who's losing? Anything, Carl, that ends up pointing to the left. And now let's walk down the entire invisible string holding them together. Let's walk down this horizontal path, writing our equation. Who's winning? We said F app 1. Then I run into F contact. F contact, winner or loser? Loser. Keep going, keep going, keep going. Oh, then I run into F contact again. Winner or loser? Keep going, keep... Oh, then I run into F applied number 2. Winner or loser? Loser. Have I included forces from more than one mass on the left-hand side? Well, then I better include more than one mass on the right-hand side. And you know what? Just as before, we'll find A, and then once we have A, we'll use that to find an individual force, like contact force. So far, so good, Noah? Gonna make it? You're a little tired. Dro is too. You awake? So Dro, I would say, oh, in this case, it's not the tensions that cancel. Those cancel. And they want me to find the acceleration. Hey, how would I get the A by itself? A is going to be F app 1 minus F app 2 divided by M1 plus M2. So Jordan, what I'm wanting you to realize is, you know what? Armed with free body diagrams and Newton's laws, even complicated stuff like this, as long as you're careful, we can break it down to, I won't call it easy, but at least fairly routine. It's going to be 42.5 minus 6.75, all divided by 6 plus 8.25. More than one number on the top, brackets. More than one number on the bottom, brackets. 42.5 minus 6.75, close it off. Divided by 6 plus 8.25. And I get 2.51. Of course, Darian, that's a rounded off answer. I'll use my answer button on my calculator because it's much more accurate. There's the first part. It said find the acceleration. Done. I'll call that part A. What's the second thing they wanted me to find? Contact force. Okay. I'm going to try and find in which one the contact force is in a winning direction. Is contact winning in mass 1 or mass 2? Oh, so can anybody see what's my equation going to be for mass 2? Yeah, which F applied? Equals M2A. So if I hear you correctly, Darian, you're going to say that the contact force is going to be M2A plus F applied 2? Is that what you're saying? You'd be right. It's going to be M2 8.25 times A 2.51 plus 6.75 27.5? Is that right? Anybody else get that? Am I right? Newtons. 27.5 newtons. That looks very messy. I can do that a little neater. Turn the page. A curling rock, rock number 1, is traveling east across a sheet of frictionless ice. It bumps another rock and experiences a force that acts briefly to the north. Okay. What will be the path of rock number 1 after the bump? Path A, path B, path C, or path D? By the way, I think path D, I don't know if your paper has it, but I think that arrow is supposed to be connected like that. Because I notice all the other arrows are connected. All right, so a curling rock, this is a top view. It's rolling along, sliding along, and it glances, it hits this rock, which gives it a force due north. What will the rock's new path be? A, B, C, or D? You know what? This is an opportunity for us to vote. Once again, how high you hold your hand up is how sure you are of the answer. Who says path A, Mr. Dueck? It's going to keep going due north. No one. Who says path B, Mr. Dueck? It's going to keep going that way. 1, 2, 3, 3. Who says, no, it's going to curve, path C, Mr. Dueck? It's going to curve that way. 1, 2, 3, 4, 5, 6, 7. Who says, Dueck, it's D? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That may be the most we've ever got voting. That's almost everybody for a change. This is a pretty good spread. A seems to be out of luck, or maybe not. So your choice is defend your answer as correct or attack someone else's answer as having to be wrong. Attack or defend. What do you think? who wants to defend their answer or savage someone else's answer as being absolutely morally wrong? Yep. Is that a hand up, Jake, or not? I saw kind of a pencil sort of. What did you vote?
I voted for D.
Okay.
B can't really be right because there's a contact force in the second rock, so it would have to apply force back onto the first rock and then in the other direction.
So, what was the path of the rock? Can you put it face down on the appropriate block? Thank you. What was the path of the rock before the collision? Due east? Was there an unbalanced force applied to it? Yes. Then there must be a change in velocity because that's the definition of acceleration. So I would say to you, no. I would say no. Thank you. So now it's A, C, or D. Any others that you think might be wrong?
It's the same reason A is wrong.
Why do you think A is wrong?
I don't know. Someone else knows.
Okay. How would I say this? Let me think. After the collision, as the rock is moving, what are the forces acting on it? Get the obvious one. Okay, gravity down. What else? Normal force up. What else?
Contact force.
After the collision, I said. After the collision. So let's think 1/10 of a second after the collision. What do you think? Oh, it's the putty. It's not a phone. You know what? That's such a distraction. I'm going to take it away. I've been watching you guys. I don't think you can play with big boy toys right now. Good physics here. It's a non-Newtonian fluid, which is kind of cool. But what's going on here? Well, what do you notice about this path's direction? Constant or changing? And velocity is a vector. All vectors are made up of two things, magnitude and. So if the velocity direction is changing, is the velocity changing? Yeah. If you have a changing velocity, isn't that another word for acceleration? Yeah. If you have an acceleration, don't you have to have a force being applied the entire time? And I'm arguing, Anthony, after the collision, there is no longer a force being applied. That would require a constant force the entire time, changing it the entire time. It's not going to curve magically. Things don't curve without a force being applied on them. They're going to go in a straight line on a steady speed. That's Newton's first. In fact, my explanation really was Newton's first law. Newton's first. We did this one yesterday. Who were the ones that got wet yesterday? Oh, of course, it was my two amigos with the putty. Okay? So example 6 we already did. I was going to try and jump into lesson 6. I'm going to save that for next week, but we're going to finish with this one. Example 7. What are the first two words of example 7? So this is harder than I'm going to ask, but this is what used to be on the old scholarship exam. It says this. Mass 2 is 12.5 kilograms. It's heavy. Mass 1 is 3.6 kilograms. Both masses are initially at rest 3.2 meters above the ground. They're both level, like in the picture. And let's be in our magic physics world, Carl, where the cord and the pulley are massless and frictionless. If mass 2 is released to fall to the ground, what maximum height will mass 1 reach? Now, the quick, obvious wrong answer, as I have kids, they say this. Look, Dueck, if you're 3.2 meters, here's the ground right here, you start to say, right, if you're 3.2 meters above the ground and you drop the heavier mass, kathunk, won't the other one go up 3.2 meters for a total of 6.4 meters? Except mass 1 is so much, mass 1? Mass 2. Mass 2 is so much heavier that here's what's going to happen. Watch mass 1. Did you notice something? What'd you notice? Did you see it? What happened to the string here? Okay. The reason this is a scholarship question is mass 1, when it gets to the top, its own momentum is going to keep it going up for a split second. How high will it get grand total? Ooh. So I think what I'm going to do is I'm first of all going to look at while it's rising under tension. Then I'll look at while there's slack in the string. While it's rising under tension, you see, well, let's look over here in free fall. In free fall. In free fall, you guys saw the string with slack in it? You know some stuff. As soon as that string had slack in it, you can tell me this. Even though it was going up, I'm telling you that. And because I asked you to find the maximum height, when we're at the maximum height, what else do you know? What is 0? Mr. Dueck, why didn't you say Vy final? You know what? Since there's only a vertical component here, who cares about horizontal? I think I could find how far it travels under free fall with the slack string if I knew V initial. How can I find V initial when we get to the slack string? From over here. From over here. Because over here, we're starting from rest. I know how far we're traveling, exactly 3.2 meters, because, Jeff, the smaller mass is going to go up by 3.2 as the bigger mass hits the ground. That's how long it's under tension for, and then after that, it's going to keep going under its own momentum with some slack. I would like to find, because I think V final when the first big mass hits the ground is V initial when the second small mass Kylie starts free falling up. What do I need? What other piece of information do I need to find V final? Ah. So, even though, Jordan, I'm going to be spending lots of my time finding velocities, really in this first situation, I'm going to find the acceleration, because if I know the acceleration, then I can go V final squared equals V initial squared plus 2AD square root, and I can tell you how fast it's traveling upwards. How can I find the acceleration? This is a job for something. Free body diagram. So I have here mass 1. What are the forces on mass 1? Get the obvious one. I got M1G. I got tension. I got M2G. I got tension. Now this is still while we're going up and going down. I know later on we're going to hit the ground and maybe there's a normal force or something, but not right now, so I'm not worried about it. Which is the heavier mass, mass 2 or mass 1? So who's winning? So my equation is going to look like this. M2G minus tension plus tension minus M1G . Is that okay? Winner, loser. Looks like a winner, but follow it around. Looks like a loser, follow it around. It ends up being a winner on this side. Looks like a winner, but follow it around. It ends up being a loser on this side. Hey, Joker, relax. We just lost tension. Why so serious? Relax. How to get the A by itself? It's going to be m2g minus m1g all over m1 plus m2. The acceleration is going to be mass 12.5 times 9.8 minus, I keep moving this line over because it's in my way. Let's try this over here, Mr. D. Minus 3.6 times 9.8 all over 3.6 plus 12.5. Can you please find for me the acceleration when we drop the big mass? In other words, can you find for me that acceleration, not the acceleration when it becomes slack, the acceleration on the way up? Can you find that for me, please? And we'll carry a few extra sig figs because this is not my final answer. Do you get 5.41739, blah, 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 blah? And again, if you're not getting this, sometime today you want to snag me about your calculator work. Is it 5.4174? Yeah? No? Not, yeah, okay. Meters per second squared. So that's going to let me find how fast mass 1 is traveling when it gets to the top. It's going to be traveling 0 squared plus 2 5.4174 times, and it's only going to travel for 3.2 meters. That's when it runs out of string and it starts free falling up, accelerating down, but free falling up. It's going to be 0 squared. I guess I don't need to type that. 2 times answer button times 3.2 square root. It's traveling at 5.888 meters per second. When the big mass hits the ground, the smaller mass is traveling up at 5.88, and now it's going to keep going for a split second. How fast? 5.888. How far? Can you give me an equation that has acceleration v final, d, and v initial in it? That's not good. Which equation? Get the d by itself. You're right. I'll give you a hint. D equals?
D equals s squared minus vi squared over 2.
Nice. It's going to be 0 squared minus 5.888 squared all over 2 times negative 9.8. It's going to be 0 squared minus answer button squared. See, Darian, I'm using my answer button because, you know, divided by bracket 2 times negative 9.8. It's going to travel 1.77 meters. So you ready? Look up. Here's the original setup. Originally, how high is mass 1 off the ground right now? What's the question say? 3.2 meters. When big mass falls, boom, how high is mass 1 off the ground right now? 6.4 meters. And then how much further does it keep going into the air? 1.77 meters before it hits the top and starts falling back down. Is that okay to visualize, Jordan?
Yep.
Okay, this is a complicated question. Although if you look at it, it's all physics 11 when I break it down. There's nothing new there. But to visualize that, Sarah, I got to agree, is pretty tough. So when it wants the total height is going to be the original 3.2 plus the extra 3.2 plus the extra 1.77. Let's write that down. The original height's going to be the original 3.2 plus the extra 3.2 plus the 1.77. 3.2 times 2 plus that. You know what? It's going to get to 8.17 meters off the ground. Mr. Dueck, are you going to give us that one that tough on a test? Nope. But in all honesty, Jeff, I would expect that most of you followed my explanation, even if you wouldn't have come up with it on your own. So I was going to try and jump into lesson 6. I'm going to pause, but I'm going to give you homework then. So I already assigned, we did number 1 last day. Number 2, take a look at the second part of number 2, please. What do you notice about the masses? What do you notice? Okay, they're m's. Now, if you don't like that, you can just make the m's 2, which means the left-hand mass is 6 and the right-hand mass is 2, and you'll get the same answer. Or if you really want to, as a nerd, Jacob, if you want to try doing it algebraically, you should find somewhere towards the end the m's cancel, and you still end up with the same answer. But if you don't like doing it algebraically, if you have an algebraic question, make up a reasonable number for the variable, plug it in. And by reasonable, don't let the mass be a trillion. It'd be yucky. 2 or 3 or 5 or 10. So number 2 is good. Ooh. 3 is tricky. See if you can figure it out. Six. I skipped 4 and 5. 8. I don't think I'm going to give number 10. Or number 9. Pause.